Yeah, it's going. Okay. Record that, right? So, Chapter 5 is all about functions. For those of you doing my other classes, you've already had this hammered down your throats. For those of you who haven't, functions are hard for students to grasp the first time they come across them, and then later they wonder why it was ever so hard. So, functions. What's a function? Well, first off, we need to remember what a relation is if we're going to talk about a function. And what was a relation? Special type of set.
A set of ordered pairs.
It's just a set of ordered pairs. You remember what a relation is? All of you who got all your answers wrong on the test about relations and the properties that they have, reflexive, symmetric, transitive. Those were properties on a relation. Remember a relation? Just a set of ordered pairs. Nothing tricky, nice and easy. Okay, so a function is just a relation with one property. What's the property? The property is that if AB and AC are in the relation, then B has to equal C. Another way to say that is, anytime A is paired with something, it better be the same thing. Another way to say that is, every left-hand element is paired to one and only one right-hand element. You can't have it paired with two things. A bunch of different ways of saying the exact same thing. You already have intuition from your lower maths what a function is. For every input, there's only one output, something like that. A function. Same exact idea. That's exactly what a function is. So here I have a bunch of relations listed. You're going to tell me yes or no, is it a function? F, is this a function? Yes or no?
Yes.
Yes.
You sure?
Yes.
Okay, she's sure. What about G?
No.
No.
Why is G not a function?
5.
We have 5 goes to 1 and 5 goes to 2. Can't have that. 5 can only go to one thing. We can't have 5 goes to 1 and 5 goes to 2. Here we had a function. What's everything 0 into? Just 1. What's everything 2 into? Just 5. What's everything 3 into? Negative 1. What's everything 4 into? 4. What's everything negative 1 into? 7. Every left-hand element is paired with only one right-hand element. Here we have the same left-hand element being paired with two different right-hand elements. So it's not a function. What about H? Is it a function?
Yes.
Oh.
Whoa! We have 1 showing up twice. It can't be a function, right?
No.
No.
It can?
Yeah.
Yeah,
It's a function?
Mm-hmm.
How many ordered pairs are in there?
2.
Count again. Just 2. Yeah, don't be confused by duplicates. Remember, in sets, duplicates don't matter. A relation's a set of ordered pairs. If you put the same ordered pair in there a bunch of times, it doesn't matter. Okay. We have some notation that you're used to with functions. Instead of us saying A comma B is in F, or A, F, B like that, like we're used to with relations, right? We have a special notation for when we're talking about functions. We say F of A equals B. F of A gives us the thing that A is paired with. A is paired with B. So when I say F of A, this is answering the question, what's A paired with? Oh, it's paired with B. That's what F of A is. Make sense? Just notation. So looking at these functions up here, what's F of 0?
1.
What's F of 3?
Negative 1.
Negative 1. What's F of negative 1?
7.
What's F of 2?
5.
Similarly, what's G of 1?
5.
What's G of 2?
5.
5.
What's G of 3?
4.
4.
What's G of 5?
Does it work? 1 and 2.
Oh, it doesn't work. What on earth? Why isn't my notation working?
This is not.
Because that notation only works when F is a function. G wasn't a function, so we're not allowed to use this notation. Doesn't make sense. And here's why we can't use that notation. What's G of 5? We don't have an answer. Make sense? So that's why we use that notation for functions and only for functions. Okay. Example. The integer function f of x is equal to x squared. You're used to seeing functions written this way as a shorthand for an infinite function. Right? So this is shorthand for this set.
Yeah.
What's f of negative 2?
4.
4. Because when you plug in -2 here, you get 4. So that's why we wrote 4 there. What's f of -1?
1.
1. What's f of 0?
0.
And etc. So I can plug every integer in here and get it square out. So how many things could I write in here?
Infinite.
How many integers are there that satisfy this relation?
Infinite.
An infinite number. So this is shorthand for this set. Another way that we could write that set is this way. It's a set of all ordered pairs x, y, where x and y are integers and y is equal to x squared. In other words, we said, we were looking at this set and we said, we know some pattern. This thing is always, the right-hand thing is always the left-hand thing squared. So that's exactly what we're saying here. What's the right-hand thing? It's the square of the left-hand thing. What's the right-hand thing of x? It's just that thing squared, x squared. That's what that notation is telling us, right? Okay. Then we have some more definitions. Definitions you're probably familiar with. The domain and the image. What's the domain of a function? In short, the domain is all the left-hand elements. What's the image of the function? It's all the right-hand elements. Now let's read exactly what I had written, but that's what it is. The domain of a function f is a set of all first elements of the order pairs in f. It's the set of all the first elements. So we take the set with 0, 2, 3, 4, and -1. And we write it as DOM of f. That's how we write the domain of f. So if I ever want to talk about that set, its domain, that's how I do it. Similarly, we have the image of a function f. It's the set of all second elements in the order pairs of f, and we write it as the image of f, IMF. That's how we reference its image. Another way that we can say that is the domain of f is equal to all the a's that have a b that they're paired with. If I can find a b such that AB is in f, then A is in the domain. Similarly, if I can find an A such that AB is in f, then B is in the image of the function. It's the same thing as saying the domain is a set of all the left-hand elements that are paired with some right-hand element, and the image is a set of all right-hand elements that are paired with some left-hand element. All right. Random stuff. So, looking back at this exercise up here, tell me what's the domain of f?
0, 2, 3, 4, -1.
0, 2, 3, 4, -1. That's it? Yeah. And what's the image?
1, 5, -1, 4, 7.
7? Okay, there we go. There's the domain of f, there's the image of f. That's what we mean by those things. Let's do another one. Let's look at f of x is equal to x squared on the integers. Let's look at this function. What's its domain?
All the x's. Yeah, all the integers.
What are they?
It's infinite.
It's infinite.
It's all real.
It's all the integers. It's all the integers, so this is just z. All the integers. What's the image of f?
Integers squared.
All the integers greater than or equal to 0. Huh?
All the integers greater than or equal to 0. Is
The
2 going to be in
absolute
here?
Of integers. Oh. Oh wait.
Come to the right some. What's the image of f? Oops, equal. It's going to be the set of all x squared where x is in z. Set of all the perfect squares. What's the smallest thing in here?
0.
0 is the smallest thing in here, right? This has 0, 1, 4, 9, 16, 25, 36. What comes next? No. Don't listen to Peter.
36.
Think in your own head.
What comes after 36?
Yeah,
49.
49. She can do 7 times 7 in her head. Okay. Next. Well, any questions so far? If you have questions, just interrupt me. I don't want to get carried away just blowing through the material. Okay, next. Let f be a function and let a and b be sets. Then we say that f is a function from a to b, provided that the domain of f is equal to a and the image of f is a subset of b. Another way that we say this is if we have f is a function from a to b, f maps everything in a to something in b. F has to use all of A, but it only has to use some of B. It could use all of B, but it only has to use some of B. Does that make sense? So let's look at some examples. Let's look at the function from the real numbers to the real numbers where f of x is equal to the absolute value of x. You know the absolute value function? What's the absolute value of negative 3? Okay. So, what's the domain of f? All real numbers. How do you know that? Because if it's a function from the real numbers to the real numbers, the domain is always going to be this entire set. The image will be a subset of this set. Could be the whole thing. Might not be the whole thing, but it could be. But the domain always has to be this whole set. Okay, what's the image of the set? What subset? What numbers? What are the numbers that this function spits out? What are all the numbers that this function spits out?
All real numbers.
Does it spit out negative 7?
Oh, all natural
Spits
numbers.
out.
All natural.
All natural numbers? Does it spit out 1/2?
No. Yes.
Oh wait, yeah, it does.
Oh yeah, it does. Is 1/2 a real number?
So does it just spit out all the real numbers greater than
All the absolute real numbers.
All the absolute real numbers. None of the
all
fake
real
ones.
numbers greater than 0,
Not including 0?
including
All the
0.
Ah, there we go. It's all the real numbers from 0 onwards. You might have seen this interval notation before. It's a set of all the numbers from 0 onwards. Perfect. Let's look at another example. G is a function from the real numbers to the real numbers by g of x is equal to x squared minus 5. What's the domain?
Real numbers. Yeah.
What? Of course it is, right? Because that's what that set is. What's the image?
Starting, all the real numbers starting from -5 to
Perfect. Almost the exact same thing. All the numbers from -5 to infinity. All the numbers greater than or equal to -5. Right?
What about the x squared? That's not mine.
The x squared matters very much.
So why is it not in there?
What are you talking about?
Never mind.
Pick a number, any number. 2. What's 2 squared? -5.
-1.
Is -1 greater than or equal to -5? Then it's in this set.
Great.
Pick another number.
No, I think I got it.
Negative
3.
3. What's negative 3 squared?
9.
9 minus 5. Is 4 greater than or equal to -5? Okay. So everything this function spits out, what are all the possible numbers? They're these numbers. Okay. Next question. Let A equal the set 1, 2, 3, 4, 5. Let B equal the set 6, 7, 8, 9, 10, 11. How many functions can we make from A to B?
Is it 6 to the power of 5?
6 to the power of 5. How on earth is she coming up with that?
Well, because she has,
Yeah, probably can. I'm just smart.
If I know that if I know that the function f is from A to B, it has to map everything in A to something in B, right?
Yeah.
So it has to map 1 to something, it has to map 2 to something, it has to map 3 to something, it has to map 4 to something, it has to map 5 to something. It can map them all to the same thing. It can map them all to 11, 11, 11, 11, 11. It can map this one to 6, this one to 7, this one to 8, this one to 6, this one to 6. right? It just needs to map everything in A to something in B. So how many options do I have for what can go here? I have 6? Okay. How many for this? 6, and 6, and 6, and 6. So how many 6s do I have? 5. So we have 5 to the power of 6 options, right?
No.
6 to the power of 5. Ah, they weren't falling for it. All right, 6 to the 5. Perfect. 6 to the 5 options. Now, in general, we're going to do exactly what you expect. Let A and B be set such that the size of A is little a and the size of B is little b. Then there are B to the A functions from A to B. Exact type of thinking. Without loss of generality, we just let A be the set 1, 2, all the way up to little a. So instead of having A as a set of A things called star, triangle, pickle, tuna, whatever, we just say we're going to call something in A1, something in A2, and there's going to be A of them. So we're going to talk about this set instead of the initial A, and it doesn't change our proof. That's what we mean by without loss of generality. Similar thing with B. A, we just made a particular set of size A, B is a particular set of size B. Then any function of the form f from A to B is going to have this form. It maps 1 to something, 2 to something, blah, 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 blah. It maps A to something, right? So we're going to have A ordered pairs, and we need to map each of the, and to complete each of those ordered pairs, we have B options. So observe that for each of the A, that's how many there are, there's A of them. For each of the A ordered pairs, there are B ways to finish it. Therefore, there are B to the A possible functions. Exact same thinking, right?
Okay.
What kind of proof is that? Like a counting proof?
Yeah, just counting proof. More of a very intuitive explanation than a rigorous proof. Okay, continuing. Inverses. Remember when we had relations, we also had inverse relations. You remember an inverse relation? What was an inverse relation?
Like the line switch.
It's where you switch all the left-hand and right-hand elements, right? We switch the 1 and the 0, the 2 and the 5, the 3 and the negative 1, the 4 and the 4, the negative 1 and the 7. And oh no, that's fine. Okay, so that's what an inverse relation is. You just flip all the elements. Well, then we can take a function. A function's a relation, right?
Yeah.
And so we can take its inverse. Our question is, well, first let's find the inverse. So let's first, then we'll ask our question. So what is, looking back over there at f and h, since those were our two functions, what's the inverse of f then?
1, 0, 5, 2, 1, 4, 7, 1.
4, 4, 7, negative 1? Okay, so there's f inverse. What's h inverse?
2, 1, 2,
2, 1, what?
3. And 2, 3.
2, 3. Right?
Yep.
Is f inverse still a function?
Yep.
Yes.
So f was a function and its inverse was a function. Is h inverse a function?
No.
So h was a function, but its inverse wasn't a function. So the question is, when is the inverse of a function still a function?
When the left hand matches to one right hand, and when the right hand matches to one left.
So when it's 1 to 1.
Yeah. So we know it's a function if every left-hand element is paired with only one right-hand element. And we know that the inverse will be a function if every right-hand element is paired with only one left-hand element. Notice here, that wasn't the case. We had the right-hand element 2 paired with 3 and the right-hand element 2 paired with 1, so the inverse didn't work. So we don't want to be able to pair right-hand elements with We don't want to be able to pair unique right-hand elements with different left-hand elements if we want our inverse to give us a function. Or another way to say that is we want our function to be 1 to 1. If a function is 1 to 1, then its inverse is also a function. So what exactly do we mean by 1 to 1? A function f is 1 to 1, and I'm going to start writing that as 1-1, 1 to 1. A function f is 1 to 1, provided that if AC and BC are in f, then B is equal to C. If two left-hand elements are paired with the same thing, A is equal to B. If two left-hand elements are paired with the same thing, then those left-hand elements better be the same thing. No, here's how I like to think about functions and one-to-one functions. It's not what the author says, but it's the way I like to think about it. So, what do we mean by a function? Here's what we mean by a function. If two inputs are the same, then their outputs are the same. That's what it means to be a function. What does it mean to be a one-to-one function? If two outputs are the same, then their inputs are the same. That's what it means to be one-to-one. You can think about it whichever way is most intuitive for you. This is personally how I like to think about it. Good? Oh, are we off the recording?
No, you're still on it.
It's probably conscious. Get right next to her. And I think we got the whole whiteboard. Yeah. Okay. So, one-to-one. That's what we mean by a one-to-one function. Here's how I think about a function. Here's how I think about a one-to-one function. Quick proof. I started the proof and then I realized it's a homework problem, so you only get half the proof.